In this lesson, we begin to consider the concept of alcohols as electrophiles in nucleophilic substitution reactions. So, at the very top, I'm going to tell you that alcohols cannot be used directly as starting materials in nucleophilic substitution reactions because OH minus is too strong of a base to be a good leaving group. So the following reaction step will not take place. You will not get a tertiary alcohol losing OH minus to give a carbocation and OH minus. You're generating too strong of a base, and this is not a good leaving group. So it gets the big red X through it. So what can we do? If that were the end of the story, this would not be the topic of a lesson, would it? But there are several strategies available for converting OH into a good leaving group. The simplest such strategy is protonation. So if we react the alcohol with strong acid, HA, the hydrogen of the acid will protonate the alcohol, and then the A minus that's left behind after the hydrogen is transferred to the alcohol serves as the nucleophile. Okay, so let's look at an example. This one's going to go by the Sn2 mechanism, and if you take ethyl alcohol and react it with HBr, you synthesize ethyl bromide. Okay, let's look at the detailed mechanism of this reaction. So step one is the new step. Protonation of the alcohol to make it a good leaving group. We're adding a step to the beginning of the Sn2 mechanism. In a previous lesson, we talked about how you can add a step to the end of the Sn2 mechanism to make when you have a neutral nucleophile to make a neutral product. In this case, we need to add a step to the beginning of the the basic Sn2 mechanism in order to turn our alcohol into a good leaving group. So let's look at this, drawing it out with curved arrows. So the lone pair on the oxygen serves as the source of the electrons. It serves as a Bronsted base. Is it a strong Bronsted base? No, it's a weak Bronsted base. But if you're using a strong acid like concentrated hydrobromic acid, you will get proton transfer from HBr to the ethanol to make protonated ethanol and Br minus. Note that the protonated ethanol will lead to water being a leaving group. Okay? If you break the carbon-oxygen bond, putting both electrons onto the oxygen, that will give you a molecule of water. And water, of course, is a good leaving group. Its conjugate acid is H3O+, and the pKa of H3O+ is negative 1.74. Once you've made a good leaving group, now using the bromide ion that got generated in the first step, it can attack the carbon of the protonated ethanol, kick out the water as a leaving group, and carry out the Sn2 reaction. We can do a similar reaction going through the Sn1 mechanism, except it's going to be one more step. So for our Sn1 mechanism, we've got to use an alcohol with a structure that's consistent with the Sn1 mechanism. So instead of a primary alcohol, we're starting with a tertiary alcohol. So in this case, our prototypical tertiary alcohol is terp-butyl alcohol. And again, if we react this with concentrated hydrobromic acid, we will get out at the end terp-butyl bromide plus water. Note that this is the reverse of the reaction that we introduced to the Sn1 mechanism with. We looked at how terp-butyl bromide will react with water to give terp-butyl alcohol. This reaction, therefore, can go in either direction, and we can drive which way we want it to go using concentrations of reactions and send it to completion using Le Chatelier's principle. So using an excess of concentrated hydrobromic acid, we'll send it to the bromide, especially if you have a way of removing water as a product. And putting terbutyl bromide into an excess of water will send the reaction to the left towards terbutyl alcohol. Let's look at the detailed mechanism of this one. Just like in the Sn2 case, the first step of this one is the same. Protonation of the alcohol to make it a good leaving group. This would be a favorable Bronsted acid-base reaction. Step 2 now is the loss of the leaving group to generate the carbocation. Again, this is a step that you should be very familiar with by this point in your studies. Water is the leaving group here. And then finally, we get attack of bromide as the nucleophile to give a neutral product. Okay, so whether we're going by the Sn2 mechanism or the Sn1 mechanism, reaction of an alcohol with a concentrated HX acid, where X is a halogen, will convert the alcohol into the alkyl halide.